Hello, everyone. I am very honored today to present our keynote speaker, Dr. Gilles Duranton. Professor Duranton is the Dean's Chair in Real Estate, professor in the Wharton School at the University of Pennsylvania. Gilles has been a leading voice in developing our understanding of fundamental issues in urban economics, such as agglomeration economies, which is the role of density in fostering productivity and creativity in urban environments, the nature of urban congestion, which is the force that offsets agglomeration in cities when proximity imposes more costs than benefits, the role of human capital externalities in cities, the effect of transportation, infrastructure, and how all of these factors interact in developing the shape of cities. Gilles has provided both theoretical foundations and empirical evidence of why and how these forces interact. He has literally written the book, or better, the handbook, on regional and urban economics, as well as more than 1 articles and book chapters covering all top economic journals. In this sense, Gilles' work has elevated the topics of urban economics to topics of general economic interest. Gilles has received multiple awards recognizing his contribution to the field. Also, he has been a leader in the profession, having served as president of the Urban Economic Association multiple times, as well as being permanent or special issue editor for all major journals in the urban economics field. I wouldn't want to let this opportunity pass without highlighting the particularly important role that Gilles has played in our Latin American region. Despite being originally French, I would also call Gilles the most important urban economist in Latin America. He has written many articles that have provided the first empirical evidence of many dimensions of urban economics topics in a region, including the costs of congestion in Bogota, the first rigorous measurement of agglomeration economies in Colombia, and the first estimation of the elasticity of trade to road development in Colombia as well. In all of this work, he has highlighted the importance of evaluating directly these phenomena in developing countries and not only to rely on existing results for developed countries. He has made this a cornerstone of his work, often participating in conferences and workshops in a region, taking multiple visiting positions in Colombian universities, and even creating a separate section in his website called Colombia Research. One example of his interest in the dynamics found in cities of developing countries is today's talk, The Fast, the Slow, and the Congested, Urban Transportation in Rich and Poor Countries. Gilles, you will have 45 minutes of an interrupted time for your talk, and then the last minutes will be Q&A. The audience can type their questions in the Q&A box in the Zoom webinar at any time during the talk, and I will deliver them to Gilles at the end. Gilles, thank you so much again. You can start now.
Okay, thank you very, very much, Luis, for those very kind words. I'm really glad that actually Luis is chairing this session, because Luis is playing a really instrumental role trying to promote urban economics and regional economics in Latin America. That was something that, when I started on this, was basically inexistent. And, you know, thanks to Luis and others, we've been having sessions at La CA, doing with mobile conferences within Latin America, and I think this is great. And, you know, thank you very much for actually playing an active role and doing all those jobs, like sending those emails and so on and so forth, so that things actually happen, looking for funding, so that we can actually build up a community of people interested in cities in Latin America. It's not that there's no problem, urban problem within Latin America. I'm actually going to show you some evidence of that today. So this is work that I've been doing with my former research assistant, who's now an assistant professor. So we started a long time ago, let me say, Protoyak Bar. Victor Couture, who was a former student of mine a long time ago, and now is at UBC, and Adam Storygard, who's been also our tireless companion on that sort of research involving, essentially, Google Maps. So here, this is a paper that we're calling The Fast, the Slow, and the Congested, Urban Transportation in Rich and Poor Countries. So what do? We are going to use Google Maps, and we're going to collect a huge amount of information, basically 600 million trip requests that we're making to Google Maps in close to 1,400 cities on all continents. Then the name of the game will be to organize this information. So to organize this information, we're going to produce first some speed indices, travel speed indices that are comparable well across countries for each of those cities. Then armed with those indices, so instead of having 600 million trips and this huge deluge of information, we're going to be down to 1,400 indices, and we're going to document how urban travel and urban mobility is actually rising with economic developments. Then we're going to decompose this effect into the effects of better infrastructure, population density that differs across rich and poor countries, and so on and so forth. Eventually, once our job is done, we will provide a global open world database on urban transportation. So again, a very, very large number of cities. Two limitations to our work or to our focus for today. I will only talk about motorized travel. I am perfectly aware that actually, in the Bogota survey, that's only about 30% of all trips. We are actually doing some work on transit, but this is still in progress. And ultimately, we are interested in something called accessibility. But accessibility, it's about mobility, what we're able to deal with today. But this is also about distances and the number of establishments and the number of possible destinations. We are working on this as well. So today, think about that as being one part of a bigger enterprise. So this is all of that is also in progress. So what do we find? We nonetheless find really interesting things. First, urban travel is much faster in richer countries. So for instance, if we compare the US or American cities with cities from Bangladesh, American cities are about twice as fast. Most of the speed variation, a very large share of the speed variation that we find is across countries, and it's all heavily correlated with GDP per capita. Then we're going to decompose those differences. We're going to decompose that variation into city level, city level attributes, trying to understand why richer countries are actually faster. And we're going to find that this is coming from essentially two main features of rich cities versus poor cities. Rich cities are less dense. They are especially more expensive, and they also have better infrastructure in the sense that they have more primary, secondary, and tertiary roads as opposed to residential roads. And there will be a little bit of an effect associated with topography. Also really interesting, those differences across cities, they're not due to the fact that some cities are super highly congested. Well, some cities are super highly well congested, and I will show you who's the most well congested. But at the same time, actually, the bulk of the variation is coming from uncongested speed, i.e., what Google tells us what would be the speed in absence of traffic, or another way to think about it, 3 a.m. or 2 a.m. travel speed. This is actually what separates poor countries, poor cities will tend to be slow and tend to be slow all the time. So why does it matter? We are interested in those issues for a bunch of reasons. Well, the main one is associated with my long-run research agenda that Louis very kindly described is, cities are about people interacting, including on the labor market. And I think for developing cities, this is actually the most important feature of those cities. They are a big labor market, and slow mobility is going to hinder those interactions, is going to put some limitations. So we need to think about that really long and really hard. And there are probably large benefits to improving those things. What needs to be said is that we're going to provide data where essentially there was none, transportation data, urban transportation data is extremely well limited. So there are some cities like Bogota who have some surveys that are reasonably well done and pretty comprehensive, but this is the exception. As soon as you look at Colombia, there's a little bit of a survey also in Medellin, which is less comprehensive and less significant. Then if you move to second-tier cities like Villavicencio, when you look at the transportation data that the city has to propose, they essentially will give you like some sort of bus map and some plans about what future will bus lines, and that's basically the information they have. So we're going to provide more. What also I would like to say is that yes, there are some indices that have been produced by private sector firms like INRIX, well, for instance, or TomTom. What we provide us is something that is fully transparent. So it's not only one number, but we're going to give you all the tools that we've developed so that you can actually, if you want to build with those numbers well differently, you will be able to. And also those alternative well indices, they tend to focus on congestion and only congestion, whereas I've just said that congestion is a small part of the story, and I'm going to show you why well congestion is actually a small part of the story. Then, you know, we are also part of the long-run agenda. Urban transportation is a policy concern absolutely everywhere. You know, urban issues tend to be transportation issues in very, very large parts, but not only, but in very large parts. So we're not going to tell you how to build well, your transportation network, how to build well your city, but we can actually come up with some description of what effective transportation networks will look like and what are the key attributes that cities need in order to improve their mobility. So in terms of roadmap, this presentation is going to be in 3 parts. So it's a big data project. So I'm going to spend a lot of time, you know, showing you how we're creating our transportation database that's comparable well across cities and across cities in different countries. Then I'm going to document a bunch of facts about urban mobility and economic development, and then we'll provide some decomposition and provide some accounting. I mean, explaining is a bit of an ambiguous word here. We're not looking at causality in our work at this point, so accounting for why richer countries are faster. So in order to have indices for cities, we need to define which those cities are, and we need to define them well consistently across the world. So this is going to be well our first step. Then we're going to create samples of trips within these cities, and we're going to query them and get the information. Then from this information, we're going to build a price index for each city. So we're going to use price index type methodologies to make sure we can actually compare oranges with oranges and apples with apples. And then we're going to use a bunch of alternative sources to enrich our data set. For instance, we're using OpenStreetMap and lots of other things. So it's going to be 4 steps for the data creation. So we're going to start with points. You know, we need to start with something. So we have a list of cities from the UN WUP, World Urbanization Project, which is giving us a list of all cities that they think exist in the world with population above 300,000. So we're going to use that we're going to use that information just as a city name and a city centroid. Then around that city centroid, we're going to define ourselves what the boundaries are. So we're not going to use the UN WUP polygons because they think they have some serious issues. So we're going to define our boundaries ourselves. For that, we're going to use data from the global human settlement layer. We're going to use a layer that is about what's being built up. So we're going to looking at all pixels that are built up. So we have pixels that are 38 meters by 38 meters. Around the city, everything that's built up is going to be part of the city, and we're going to draw a 500-meter radius around those points, and that's going to define our cities. Then there's been months of work to address this bullet point here. Months of work because we wanted those cities to be done properly. So for instance, if Soacha, which is a big suburb just outside of or part of Bogota, is according to WUP a different city, we're going to remerge it with Bogota. On the other hand, you have cases like San Francisco and Oakland, where if you draw origins and destination in San Francisco, Oakland, which was one city, according to the World Urbanization Project, you're going to end up crossing the Bay Bridge many, many times, and probably way too many times. So we want our cities to be somewhat monocentric. So we're going to detach Oakland from San Francisco, which is a very big job. So once we've done all those things, we are left to close to 1,800 cities. Then some bad news, we want to cover the world, and unfortunately China, South Korea, and North Korea don't want much to do to have with Google Maps, so we cannot get real-time well travel time well data for those countries. So we're going to be left with close to 1,400 cities. Then once we have, so now we have our cities, we have, we've defined them with specialists. So then we want to have trips inside those cities. So we don't have a travel survey for all the cities, only for a very, very small number of them. So we're going to design trips for all those cities that resemble actual trips. And then we will want to do that maybe in different ways, using different strategies to verify that we get the same result. So what we're going to do, we're going to follow the same sort of strategy that we've used before for India. The first type of trips we're going to define are radial trips. So we're going to take some points close to the center, let's say within a kilometer plus of the center, some point further away where there's some built up, and we're going to define an origin and a destination, or a destination and an origin. So those trips are essentially commuting trips in a standard monocentric type framework. Then, given that we're playing with the geometry of those cities, we're also going to define trips that go from one part of the city that is built up and try to go 20 degrees northwest or southeast. We're using a circumferential type of approach, i.e. part of a circle. Then we're also going to take some points that are built up where we are going to distribute trips around that point in a gravity type fashion towards other built up points and following a distribution of distances, which is very close to the one we observe either in the US or in Colombia. So that's basically a truncated distribution with unit shape parameter that we're going to truncate to avoid the fat tail. Then finally, we're going to, following also what people do or what we observe in travel surveys, a breakdown of trips, going to workplaces, going to schools, going to all sorts of points of interest, hospitals, churches, mosques, and so on and so forth, you name it. For each city, we're going to define a number of trips, which is basically going to be the screen. We're proportional to the square root of its population, so that even in small cities, we have enough statistical power. So this is an illustration for Lagos, Nigeria. So this part of Lagos is actually water. Here, that's normal. And here you have the sea. So all of that is normal. So this is the distribution here of radial trips. Here, this is a distribution of circumferential trips. So yes, we're going to miss this bit of Lagos for those trips because there's not quite enough to do 20 degrees or more. We've selected places with some locations with big establishments, so we're calling that work. So this is a sample of trip to works, and here this is a sample of trips to school. Note that we are using Google Maps, so here we're not trying to play with Google Maps too much and transform the data. Google Maps is indicating the first choice of Google Map is going to be a combination of being near and being popular. That's the one we're going to take. So all in all, for all of our world cities, that's going to lead us to define about 20 million trips. And we're going to query each trip about 30 times. So 15 of those times are going to be over 2 weeks exactly at the same time, so that we can also talk about reliability. I'm not going to do that today, but this is also part of our pipeline. And the other times are going to be drawn according to some distribution that corresponds to what we have in travel surveys. We're going to oversample the night slightly so that, again, we have enough power even at 2 or 3 a.m. But then we're going to reweight when we do our regressions according to either the US travel survey or some other travel information that we have. So we're going to do that on Google Maps. We're going to use the website and not the API because we're making a very, very large number of queries. That's difficult on the website, but possible. On the APIs, that's just prohibitively expensive. So in order to do that, we're actually going to leverage on Amazon Cloud. where we're going to rent large number of IPs and make sure that the logistics of that works so that we can query all our trips at the time we want to query them. So we're going to ask Google real-time travel times for motorway vehicles for this particular origin and that particular destination. That's a trip instance that belongs to a particular trip. We've done that between June and November 2019. We resumed our queries in March 2020 at the beginning of COVID, so at a slightly slower pace, but we've been collecting another billion observations since then. I'm not going to talk about them today, but we also have another billion observations to handle in the future. So for each trip, we're going to use the recommended Google Maps route, and we're going to get traffic duration and expected traffic duration and the length of that trip. That allows us, of course, to compute travel speed. Then Google is also telling us what would be with the duration in a state with no traffic. So we're going to call that uncongested speed. And we've made sure that uncongested speed is actually highly correlated with whatever was the fastest instance of trips with 3 a.m. speed and so on and so forth. For each trip, we also collect the recommended routes for one instance, i.e. all the waypoints along that trips, so that we can reconstitute the routes being used, which type of road, which class, and so on and so forth, how many intersections, how many left turns, how many right turns, and so on and so forth. So here's what the slightly processed data looks like. So here we're looking at a bunch of cities. So the title is the fast, the slow, and the congested. So the fast, or at least for the fastest, that's going to be Flint, Michigan. So you see that Flint, Michigan, you can travel at close to 50 kilometers per hour throughout the day. That's going to be our fastest city. No big surprise, maybe, it's a city with very good infrastructure that was planned for several million people, that has had all sorts of industrial issues, that has been losing population. So it's a sort of place where you can drive very easily and very fast. Then the congested, so the most congested place is going to be Bogota or West City, where unfortunately we cannot be today, where at night you can travel around 35 kilometers. But during the day, you see, and throughout actually most of the day, travel is much slower, whatever between 15 and 20 kilometers per hour on average. Then the slow, that's going to be Dhaka, Bangladesh, and lots of cities like this, where you see this some amount of congestion, but not that much actually, it's just very slow, even during the night. Dhaka, Bangladesh, you cannot go much beyond 20 kilometers. And the very last line is actually the center of Dhaka, which is even slower, of course, than the whole of Dhaka, and has slightly more congestion in the sense that speed during peak hours is actually much slower relative to the fastest time of the day. So that's what our data, when we process it and aggregate it slightly, looks like. So how do we know this is good quality data if you've not been convinced by my previous slide? The first one is, our first argument is that, Google Maps is the most popular mapping navigation app in the world. The market has been talking, people use it, or people use a close neighbor, which is Waze, that relies on the same sort of data and that actually also belongs to Google. Then what is the data made of? Google is a bit of a black box, but we know they rely on GPS pings from Android cell phones and other Google Maps users. We're talking about 2.5 plus billion people actually providing information through their cell phones to Google Maps at the time we started our queries in May 2019. Still, there are some worries that Google may be spending a lot of time and effort trying to process the data properly for cities that matter, cities with a big customer base for Google, people who are traveling a lot and so on and so forth, and maybe the quality of the information for poor cities is less. So we're going to be slightly obsessive about that. So let's do a number of external checks. First, we can observe that everywhere in our cities, nearly everywhere, like 99 points or something %, there's actually cell phone coverage, and typically third or fourth generation cell phone coverage. Then in our previous paper for India, what we did was to work with an external provider, developing an app and bribing drivers to use it so that we gathered data for about 100,000 trips. And we checked that those trips against Google Maps, and it worked really well. We also checked our Google Maps data against data from Uber, which has been released for a number of cities all over the world. And we've also been checking mobility outcomes during public holidays, strikes, and so on and so forth. All those events, making sure that actually, yes, in that very city, on that very day, and sometimes in that very part of the city, there's something happening to mobility which is abnormal. Sometimes it's abnormally fast when everybody's home. Sometimes it's abnormally slow when everybody's out. We've also done a number of internal checks on the data. So our main metric is we're going to look at the share of trips for which there's little to no variation between the slowest and the fastest instance. So we're going to use that as a way to measure data quality. We do expect some variation, even in places where there's going to be very, very little congestion. We do expect some variations throughout the day. If we don't observe any, it might be a sign that there's something suspicious. So we're going to eliminate the bottom 10% of cities with the least variation. In some alternative samples, we can be even more conservative and eliminate whatever the bottom 20 or 30% if we want, or alternatively, keep everybody. So now that we've done this, we want to compute a speed index. So we want that speed index to be comparable across all cities in the world. The problem is that trips will differ in systematic ways across cities because they will probably tend to be a bit longer in larger cities, a bit further away from the center, and so on and so forth. So we want to actually condition out all those differences. And for that, we're going to follow what we've done before in other papers, either with Victor and Matt Turner or with the same set of courses. We're going to think about a price index methodology where we're going to consider that each trip is a good, and speed is basically the inverse price. Speed is basically how much time you need to spend, so how much distance will you cover per unit of time, so we can recover very easily the amount of time it takes per unit of distance, and we're going to think of that as a price. And then we're going to make sure we can be comparable across cities. So how do we do that? We have trip I in CTC, and we're going to look at the speed outcome of for trip I, which we're going to regress on a bunch of characteristics of trip I and a fixed effect for CTC where trip I is going to take place. So what are the first outcome when we consider is speed. So the speed indices we're going to estimate here is going to be a true speed index S of CTC. We're also going to use as an outcome on the left-hand side uncongested speed. And uncongested speed is going to lead us to an index of uncongested speed per city. And finally, we're going to think about congestion, and we're going to define congestion as being the log of uncongested speed minus log speed. So that's going to be the log of a delay between what you could achieve and what you actually were achieving. So what do we put in our controls? We're going to put trip distance, distance to the center, trip type, because we have different types of trips that we've designed, time of day, day of week, and weather conditions, because we can recover the weather conditions in that particular city at that particular time. So our indices, they're just fixed effects. They're reasonably simple indices. We've been computing, at least for India and the US, alternative indices, last pair and patch type indices, or we've also been computed logit CS type indices as well, and they're all pretty highly correlated with what we do. So now that we have this, and taking advantage of the fact that actually log speed is log uncongested speed minus log congestion, our fixed effects are going to be separately additive. The fixed effect for speed is going to be the difference between the fixed effect of uncongested speed and the fixed effect of congestion. So we can actually do some variance analysis here and decompose and decompose well the variance well pretty easily. So when we do our trip level regressions, this is what the world looks like. So let's actually focus on our baseline regression. So all trips, we're going to regress speed on trip lengths. So you see that trip length is actually a pretty strong determinant of street speed. Trips that go further away will be faster to some extent because well, they use faster roads, but also for perhaps for a bunch of different reasons. Trips that are further away from the center are going to be also faster. We're going to estimate velocity effect. This is actually the object of interest. We're going to condition out, as I said, workday, work well of the week, focusing only on weekdays. We're going to weight according to the NHTS for the US survey, and we will also well control for weather conditions. So you see that we have an R square of 0.165, which is not bad at all. So this is going to be our baseline. In more sophisticated regressions, we are going to also condition out the gradients up and down of the trip, because we can well compute that. The composition of the roads, so we will have whatever 6 or 7 road categories, and we can verify that trips on highways are faster than trips on primary roads, themselves were faster than secondary roads, and so on and so forth. We are going to be able to condition out also the number of left turns, the number of establishments being passed, i.e. the density of stuff around the trip, city effect again, and so on and so forth. So that's going to lead to higher square. So we're not going to use, so the results of that, that regressions are really interesting, but we're not going to use them here because we think that actually some of those characteristics are actually part of the city effects that we're trying to condition out, that we're trying to measure. So we don't want to condition that out right from the start. So showing you some results about those fixed effects. So who's fast, who's slow. Think about those, so those indices are basically in log relative to the average. So the fastest city in our sample of, so the winner among whatever close to 1,400 cities is Flint, Michigan. And you see that actually all the fast cities that we have, except for this lone exception from Saudi Arabia, they're all American cities, and they're all small. They're typically Midwestern or Southern cities. Then who's slow? Maybe no big surprise. So the slowest city is Dhaka, Bangladesh. Lagos is also very slow. So is Manila. So is Calcutta. So you see large, very large, developing city from poor countries. Bangalore, Dar es Salaam, Jakarta, Lima for Latin America. So very large cities, or maybe smaller cities. Well, if you look at India, Bhiwandi, Bihar Sharif, and Patna. So Patna, it's in the northern part of India. It's in Bihar. That's actually, it's a mid-sized city. I mean, it's still whatever 2 or 3 million, but it's very, very poor. So is Bihar Sharif. So you see that it's going to be a mixture of being like really big and perhaps somewhat congested, or being in a very poor country and being mid-sized with very, very bad infrastructure. Who's congested? Who's not congested? So Bogota is the host city. And Bogota is actually, according to our measurements, the most congested city within the world, followed by some Russian cities. Then maybe no big surprise, Manila, Bangkok, Bangalore, Mexico City. The first European city is London, Lagos again, Mumbai, New York showing up in the top 20, Panama City and Nairobi and Delhi. So you see, maybe that ranking is not that surprising, and this is what we find. Who's not congested? So who's much faster than the average and with less congestion? It's basically all smallish city in Africa. Some of them, places like this, actually you cannot access them from the outside world. So it means that every vehicle needs to be shipped perhaps by plane or something like this. So you have very, very few vehicles in those places, and the amount of congestion you have is extremely limited. Then in terms of uncongested speed, i.e. the speed you can achieve when there's no traffic, the speed you can achieve typically at 2 or 3 a.m. in the morning. Again, a whole bunch of American cities. Flint is still the leader here. and who's very slow, very poor places in India, Bangladesh, and Africa. So, conclusion from that first analysis, there's a lot of dispersion. The fastest city is actually about 3 times faster than the slowest, right? We have more than a log point well difference between all the cities. Most of that variation is actually coming from uncongested speed. So this is a really important result. 90% of that variation is coming from uncongested speed. You're going to tell me, yes, but you're looking at very big cities, you're looking throughout the day. Even if we look at the center of the cities, even if we look at only peak hours and so on and so forth, you know, it's no longer 90%, but it goes down to like maybe 84%. So it's still a lot of that speed well variation that we observe in the world is actually coming from uncongested speed. That result also holds within countries. We're showing that for India in another paper. And that's probably well telling us, you know, in a loose way that infrastructure investment for transportation in cities is really big deal. And maybe we should focus more on this than congestion. So congestion, I'm not denying that this is really important, especially for our hosts in Bogota, but this is still an order of magnitude less important way to explain variations in mobility across the cities. It's mostly about uncongested speed. So who's fast and slow? As we said, the US has 87 of the 100 fastest cities out of 139 US cities in our sample. At the other end, Bangladesh is actually the slowest country, with all 9 cities in Bangladesh being among the 15% slowest. So this is the first part of our database, and we're going to aggregate that with OpenStreetMaps, where we can measure the roadway by road class for the whole city and for each trip that we have. So that allows us to measure like the road network, how grid-like it is. So we call that gridiness, the length of blocks, the average number of streets per intersection, and so on and so forth, whatever you like. We can actually measure with the things. OpenStreetMap is also very useful to measure water within cities, either coastlines or rivers or lakes. Then we're also going to use WorldPop with population given 90 meter by 90 meter pixels. That allows us to compute total population and some variants of that, like average population that you have within 3-5 kilometers, but we find actually that total population is doing a good job, and also some measures of how concentrated or dispersed the population is within the cities. From our boundaries, we can compute areas, of course, and follow what my colleague Nina already did, and get some measures of good shape or bad shape of the cities. So we have a bad shape index that is basically using exactly the same metric as Nina, and aggregate them well together. Then from Google Maps, we can also, from the API this time, we can also measure the elevation at all intersections. So we can measure how up and down trips are going, but also how the whole city is hilly or not. So these are 2 cities that we have on OpenStreetMap, Ciudad Obregón in Mexico. That's actually the city which is the most grid-like, and you can actually see it from that map. And then at the opposite end, the least grid-like city in our sample is Charleroi in Belgium. It looks a little bit like Belgian politics. It's very, very messy. So more in terms of city attributes, we're going to get city level GDP per capita data, but only for a bunch of OECD countries. We're going to use for our 2 biggest countries, India and the US, we're going to use the National Sample Survey and the American Community Survey for the US. That's going to give us aggregate income for the cities, well measured, we hope, reasonably well. From the World Bank, we're going to get GDP per capita at the country level, and then we're going to use a bunch of other things, like, for instance, a global preference survey that's going to tell us about a risk-taking index, which may be correlated with city-level driving behavior. So how do we think about all those issues? Is the following. We have, at the upper end, we think the level of development is going to matter. Maybe there are some other high-level factors like colonial origin, legal origin, some cultural features, and so on and so forth. That's going to affect a bunch of factors, some of them that we observe, so we call them the direct factors, some of them that we observe, like the infrastructure, like other city characteristics, and then a bunch of other factors that we don't observe very well, especially on the demand side, you know, the vehicles, driving behavior, will of people, and so on and so forth. All of that is going to affect what we call uncongested speed and congestion, which in turn will determine the travel speed. So that's the way we're thinking about that. So we're going to make some measurements directly from this to there, and then try to see how much of the effect from the top to bottom we can actually explain going through those intermediate factors that we observe. So that's an accounting exercise that we're doing here. So here's the sort of exercise we do. So what we're doing here is we're going to use the speed indices that we've estimated before, and we're going to regress them on stuff either at the city level or at the country level, clustering the standard errors well properly, and so on and so forth. So if we just do a regression on the city fixed effects, actually we get a R square of 71%. So that's telling us that, sorry, on country fixed effects. So that's telling us that a lot of the cross-city variation we have is actually a cross-country variation. And interestingly, if instead of using country fixed effect, we use country level with GDP, that's going to actually still have a pretty high R square of 44%. So we're going to explain about 60% of the city level, of the country level effects that we were measuring before. If we focus on the OECD sample, which is much, much smaller, you see that we're still finding the same sort of effects. If we go down, because well, the advantage of our OECD sample is that we have city level GDP measures. So you see that it's not changing things very much. What's interesting is that when we combine city level GDP variable with a country fixed effect, so we measure the effect of GDP per capita within country, you see that now the sign is actually opposite. So country level GDP is really useful to measure what's going on across cities. But when we go into city level GDP, there are some effects that are national level development, but also within country, some effects that maybe we're going in the opposite direction. We know that in the countries like the US, for instance, where the funding formulas for infrastructure actually will favor cities like Flint, Michigan, small southern cities, and so on and so forth. So they're going to get a really good infrastructure. Actually, when we do the exercise for the US, there's a strong negative effect here. So we think of city, country level GDP being really important to determine travel speed, but within countries, things tend to be more complicated given how infrastructure is allocated. So for India, so for the US, it's a strong negative. For India, we find nothing. Actually, when we look more carefully, what we find is a bell shape, effect. So now that we have this result that it's a lot about country level GDP, what we want to do is to decompose this effect into the effect of all the city level features, all the city level attributes that we have. So we're going to follow Gelbach 2016, and we're going to do the following decomposition. First, we're going to do the regression I just showed you in the second column, regress speed on GDP per capita. And that's going to give us this coefficient beta 0. So that's going to be the growth effect or the growth association between speed and GDP per capita. And then we're going to run the full regression which I've not showed you yet, which is speed on GDP as well as all city attributes that we have. So we're going to estimate for GDP a second coefficient beta 1. And then we're going to estimate a bunch of coefficient gamma for all those other attributes, city population, city area, the amount of infrastructure, blah, 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 blah. Then we're also going to estimate this auxiliary regression when we're going to regress each attribute on city level GDP, and we're going to estimate those gamma coefficients. Then, property of ordinary least square, we can actually write the coefficients in the original regression. So the point 13, this point 13, we're going to decompose it into a residual effect beta 1 in the full regression, and the effect of all the other well variables, which is going to be measured through both the coefficient, how important well they are well to explain speed, and how closely related well they are with GDP. And we can measure the share of each CT attribute to explain differences in speed between rich and poor countries. And that's going to nest, into our other decomposition of congestion versus uncongested speed. So here's the result here. So this is the regression I showed you already with, in the base regression, this coefficient of 0.13. And then in the full regression, the coefficient is much lower. So this is the residual effect. And then we have a strong effect of log population. So keeping area constant, you increase population, that's going to reduce speed by quite a lot. Keeping population constant, increasing areas, that's another effect of essentially population density, that's going to be associated with a higher speed. Worse shape, you're going to drive faster. More population concentration, i.e. some areas of concentration and some areas which are more empty, that's associated with our data with faster speed. Elevation variance, so being more hilly, slightly slower speed. So here with the heterogeneity is that it matters more in developing countries, matters less in rich countries. There's a little bit of an heterogeneity because rich country can actually throw money at bad geography. Same thing with water. That's going to be associated with slower mobility overall because it means having more rivers, having more coastline, and so on and so forth. All those things that tend to be associated with slower mobility. Roads, we have, so primary, secondary, and tertiary roads and highways, we have an elasticity of about 12.06. And if you followed some of my previous work, here this is the same regression for uncongested speed and the same regression again for the congestion factor. And we find actually that this is associated with being able to travel faster, maybe in a more direct way, as opposed to reducing congestion, which I guess I take as an indication for some other work that we did with MapTurner. And then how grid-like the network is, that goes from 0 to 1, and you see that this is a pretty large effect.
Jill, it's 12:35. If you could start wrapping up.
Yep. So I'm nearly done. So you see that here we have this 71% this 71% R square. So when we do the decomposition, we see this is about population and area, i.e. with density, and major roads. So richer cities tend to be faster because they're less dense and they have more roads, and most of that contribution goes through uncongested speed and not through congestion. So we can do the same exercise also trying to explain why the US is faster than the rest of the OECD. Actually, when we control for everything else, the US effect has disappeared. So the US effect can be explained by American cities being more expensive, lower density, and having a road network that is more grid-like. Then we can also try to explain why Bangladesh is slower than even a sample of poor cities. It's slower because actually even for the developing world, Bangladesh actually has super dense cities and is lacking road infrastructure. So conclusion, we've developed an urban transportation database that's comparable across all cities, across a very large number of cities within the world. We hope that this data can be useful for future research. We've identified some robust correlates of travel speed within and across countries. We find that rich countries are significantly faster than poor countries. That's an important feature where we think of economic development, and this is associated with better infrastructure and less density in those cities. And this is about roads and your ability to move in absence of congestion and not about congestion. So thank you very much.
Thank you so much, Jill. This is great work, very interesting. I can't wait to have access to hopefully the database when you share it as you publish the paper.
Yeah, the paper is published to give some incentive to referees.
Yeah, exactly. There is there are a couple of questions here about your presentation. So first thing, let me rephrase this to summarize a couple of questions that are related. Um, you use public transportation information in Google Maps, and I would add to that, it seems in your ranking of fastest cities, we have American cities, some Middle Eastern cities that are known to be very car oriented. So should we understand this almost as a defense for car transportation? If you want to be fast, you should focus your transportation on car.
Yes, I think so I haven't showed you anything about transits. So we measure transits through Google Maps. So it means that this comes with a lot of limitations. Essentially, this is official transits, and this is based on transit schedules. So in many parts of the world, you have big informal transits, which we're not able to measure. So we actually, at the moment, we're looking at alternative measures of transit so that we can capture that as well. But what we know is that transit is typically slow. Indeed, among the fastest parts of the world, it's all about those places that tend to be very car well oriented. Maybe this is not very surprising. Transit results again are yet to be forthcoming with the caveats that I've put, but we already know that transit indeed is slow. The key here is that, again, being able to go fast is one element. The other element that we haven't tackled yet is your ability actually to go fast, but also to be able to access lots and lots of places. So Michigan is actually, Flint, Michigan is not maybe the most attractive city within the world because you may be able to go really, really fast, but it also really well depends on what you can access. And in Flint, there's actually not that much to access. So we are completely well cognizant of that. We're actually working really hard to actually gather data about all points of interest within the world so that we can actually put that together with our mobility data. But we think, we need to take a longer look at mobility, and this is part of that exercise.
Yeah, that is precisely another related question, which was, and I think referring to Flint specifically, have you thought of building this composite index of access to jobs, or even more simply, since you have that information on population, access to other people? We would want to have speed to access increase interactions. And if you are in a place with very low population, very dispersed population, maybe similar speed is getting you the same amount of interactions as you would get in a denser place like Bogota.
Yeah, we completely agree with that. So we've done some preliminary analysis, and believe it or not, accessibility is also better in the US than elsewhere, because in the US you also have lots of points of interest. But at the moment, we're actually recreating those points of interest, but to make sure we actually capture everything as much as this is well possible. So yes, in terms of welfare, the preoccupation is accessibility. Accessibility, it's a whole other paper. So we've developed a framework to think about that. So you need to think about two other things for accessibility. You need to think about not only how fast you can go places, but how far they are, and really hard, how many of them, and how substitute will they're going to be, how much choice will you have. So all of that we need to think about, so we want to think about, but think of that paper as whatever step number 1 of 3 or 4. We're not quite sure whether transit belongs to that paper or is its own separate paper. And we know accessibility, we try to present everything with accessibility, it just doesn't work. We don't want to write a 200-page paper, so we're going to try to write 3 or 4. And accessibility is certainly going to be a big part of that.
Since you're already building these different types of trips, it would be very interesting for that future work to see the difference in speed in trips going, to downtown and city centers where most of the jobs might be located, versus the radial trips or that going around the circumference. So there's all this work about market access in cities, for example, the effect that Transmilenio has had in Bogota on access to jobs. So that would be very interesting to see. It's related to the work by Nick Tsivanidis and all these spatial equilibrium models.
So here, that's also part of what we want to do. So we resumed our queries in March 2020 for the entire world again. So we think we have enough power to measure each city on a weekly basis. So for instance, we can do things like Paris just lowered its speed limits to mostly from 50 kilometers per hour to mostly 30 kilometers per hour. We can try to measure what's the effect of that. We have data, so if people are interested, they can approach us. We won't be able to say yes to every project, but we know there's a lot that we can do. And in related work, we're actually focusing on 10 cities in Asia where there will be BRT or MRT projects, or like in Manila also, like a major tunnel that just opened. We've been collecting data to measure what is the effect of those things, and we will have a lot more data. So Nick Tsivanidis did some great work. Here the idea is we'll be able to measure all the trips, those that are directly concerned by the transportation improvements, but also try to see if we actually do observe those general well equilibrium effects that should actually modify the equilibrium for the entire city. Do we actually see that?
I think we have time for one final question, which is more, I guess, a big picture and forward looking. And it says that COVID-19 changed our view about whether mobility is required or not for productive activities. Have you studied how the relationship between congestion and productivity has changed since the pandemic? Or do you have any ideas related to that?
That's a great question. Let's be humble on that one. I mean, like many other questions, we are able to measure what happened everywhere in the world during COVID. We are not completely sure exactly how we want to handle that. Being able to measure the relationship between mobility and productivity, yes, I'd like to be able to do that. I think people have tried to do that. Nobody has been super convincing so far. What we can do is look at the evolution of what's happening during COVID. What we observe, I mean, preliminary results, we took some peeks into the data just to make sure that actually what we're collecting is making sense, and that we're not spending whatever, like $1,000 we're collecting, but that sort of stuff every month, well, for nothing. So what we're seeing is that actually congestion has come back in many parts of the world, has come back, and maybe actually whatever we're converging to an even higher level, while at the same time, indeed, the data is telling us that in at least many parts of the rich world, people are commuting less. So this is associated with reclaiming the roadway for restaurants, for bicycles, and so on and so forth. But it looks like, this is not coming freely. This is also creating some congestion. So there'll be some thinking to be done. I think with the sort of information we can provide is also useful for that sort of question. Is just that, we're doing a lot of hard work and we want to do it well. So we're spending a lot of time checking every single step and stuff. So there's only, this is our second paper. We have 2 or 3 more in preparation, but hopefully we'll also be able to get to questions like this.
Thanks so much, Gilles. This is very interesting work. And as you have just discussed, is part 1 of what will become, I think a reference data set and a reference work for everyone studying different dimensions of speed and congestion in cities. Unfortunately, there were a couple more questions that we couldn't get to. There was a lot of interest in the talk, but we need to stick to the schedule of the larger conference. So thanks again, Gilles, and thanks everyone for connecting. I hope you continue following the next events here at LACEA.
Okay, thank you very, very much for having me. It's been a pleasure to talk about this. And again, if people are interested with the data, they can come to us.